Hello everyone, welcome to the lecture of CMoS Inverter. In the previous lecture we have seen NMOS Inverter, now we will see CMoS Inverter. We are going to understand the CMoS Inverter operation and its characteristics in this lecture. The contents for this lecture are starting with CMoS Inverter circuit diagram, construction and its operation, then deriving of its transfer characteristics and deriving its sizing. The circuit diagram of the CMoS inverter is this. Already we have seen this in alternative pull-ups. The circuit diagram is having of NMOS transistor and PMOS transistor, and PMOS transistor gate and NMOS transistor gate are connected and input is applied at the gate terminals, and drain of the PMOS transistor and drain of the NMOS transistor is connected and output will be taken from that point, and source of the PMOS is connected to VDD and source of the NMOS is connected to the ground. So this is the construction of the CMoS inverter circuit. With 4 terminals it is represented, with 3 terminals it is represented. Here, when designing with the CMoS inverter, the logical approach is use NMOS transistor in the pull down path and PMOS transistor in the pull up path. So here this PMOS transistor is calling as pull up and NMOS transistor is calling as pull down transistor, because the output is pulling down using this NMOS, output is pulling up using the PMOS transistors. This is the construction of the CMoS inverter circuit. Let's check its operation. When Vin is equal to logic 0, what will happen? When Vin is equal to logic 0 at both gates, logic 0 is connected. So because of that, NMOS transistor is off and PMOS transistor is on. Since PMOS transistor is on, it is acting as a short circuit, and NMOS transistor is off, it is acting as open circuit. Since it is open, output is not connecting to the ground. Since it is short, output is connecting to the VDD. So when Vin is equal to 0, PMOS transistor is on, PMOS transistor is on and NMOS transistor is off. Therefore, V out is equal to VDD. Here, PMOS transistor is representing as T2 and NMOS transistor is representing as T1. Therefore, when input is equal to logic 0, that is represented as A, here V in, T1 NMOS transistor is off and PMOS transistor is on, output is equal to VDD. Then, when Vin is equal to VDD, that is for logic high, NMOS transistor is on and PMOS transistor is off. Therefore, pull up path is open and pull down path is shorted. So, output is grounded. So, when Vin is equal to logic high, that is equal to VDD, NMOS transistor is on and PMOS transistor is off. Therefore, output is equal to connected to the logic 0. That is, PMOS is off and NMOS is on. Since NMOS is on, the output is having of discharge path to the ground. Therefore, V out is equal to 0. Here, output of VDD and output of 0 are strong values. Strong VDD and strong 0. Since in the pull down NMOS is used, NMOS passes strong 0. And in the pull up PMOS is used, PMOS passes strong 1. So, both output logic levels are full swing. Both output logic levels are full swing, and when input 0 is applied, output is equal to VDD. When input VDD applied, output is equal to 0. Therefore, it is acting as inverter circuit. that is NOT gate. This is the operation of the CMoS inverter. Let's see its static behavior of CMoS inverter. Its behavior, it is having of high noise margin because we have seen both outputs are full. So, output full swing is the higher value, stronger value. Therefore, it is having the high noise margin ideally equal to supply voltage, that is VDD. Then it is called as ratio-less logic circuit, means outputs are independent of the sizes. Then its output impedance is low, that is less prone to the noise. And its input impedance is high, it is having a high input impedance, therefore it provides the improving fan out. And here there is no static power consumption because of open in the either pull up path or pull down path for both the input values of 0 and 1. For any input there is no static connection between the two power rails, therefore no static power consumption. This is equal to 0 in the CMoS. This is the static behavior of CMoS inverter. Let's see its transfer characteristics. How can we get the transfer characteristics of this CMoS inverter? By applying different values of A at the input, by having the output, we can plot the transfer characteristics. That is output versus input values. To draw the transfer characteristics, here we want to see the inverter operation as 5 different regions and its output equations. So, take the T1 transistor as NMOS, T2 transistor as PMOS. Input A is changing like this 0 to 5 volts. While changing 0 to 5 volts, we can take this as 0 to 1 volt by assuming 1 volt as VTN. Then 1 volt to 2.5, 1 is taking as VTN and 2.5 is taking as VDD by 2. So, VTN to VDD by 2, and the third region we are taking as 2.5 volts, that is at VDD by 2, and now VDD by 2 to we are taking as some 4 volts, that is VDD minus mod VTP value, and then taking from 4 to 5 volts, that is VDD minus mod VTP to VDD value. Therefore, 5 regions taking as region A, region B, region C and region D and E, taking as 5 regions of these values, that is 0 to VTN, VTN to VDD by 2, VDD by 2, VDD by 2 to VDD minus mod VTP and VDD minus mod VTP to VDD value. Like this, taking the 5 different regions 0 to 1 and at 2.5 and to 4 and then 4 to 5. So, region A, region B, region C, at this point region D and region E. We are taking as 5 different regions to make understanding of this inverter to draw the transfer characteristics. Now, this is A to E. This is important. The region of operations means division of input voltage and checking the conditions of T1 and T2 operation. To know the operation condition of T1 and T2, we have to know VGS and VDS values. So, VGSP, then VDSN and VDSP. After knowing of these 4 equations, we can tell either T1 is in the SAT or non-SAT or cutoff. Similarly, T2 is also in the SAT or non-SAT or cutoff. So, what is the equations? What is the VGSN? VGSN is equal to always whatever the voltage applied here as Vn. Therefore, VGSN is equal to Vn always. This is the equation 1. Then, what is VGSP? VGSP is equal to gate minus source. At source VDD is applied, at gate Vn is applied. So Vin minus VDD is the VGSP. Take that as equation 2. Then V out, that is VDSN. VDSN is equal to simply V out. So V out is equal to VDSN. Take the equation number 3. And VDSP is equal to VDSP, that is at a drain and source. This is the V out minus VDD. So VDSP is equal to V out minus VDD. Take the equation number 4. So these 4 equations represent the transistors T1 and T2 are in cutoff, saturation and non-saturation. And for the cutoff, saturation and non-saturation, what are the equations or what are the voltage conditions? For cutoff, VGS is less than VT, and for non-sat, VGS should be greater than VT and VDS should less than VGS minus VT. Then for the saturation region, voltage conditions are VGS is greater than VT and VDS is greater than or equal to VGS minus VT. So by following these equations of voltages, the transistors T1 and T2 will be defined whether those are in the saturation and non-saturation. Having these conditions and finding the values of VDSN, VGSN, VGSP and VDSP, transistors can be defined either in the sat or non-sat for the regions of region A to region E. After knowing this, we can draw transfer characteristics easily. So, see all these 5 regions of operation like this. So, region A to region E, the voltage conditions 0 to VTN, to VDD minus VTP to VDD, 5 regions of voltages. Now, equivalent values if the transistors T1 and T2 are in linear cutoff, linear sat, sat and etc. means the transistor operations based on the equations of the above set. Now, the output values for the inverter are these. Means, these 5 regions, if we have taken our CMoS inverter and by substituting the values of input, different values of these 5 regions, then the transistors of NMOS and PMOS will be in these regions. Then output voltage will be provided of this, and for these regions equivalent circuits are represented here. The first is region A, where in that region A input value is 0 to VTN, then NMOS is off. NMOS is off means NMOS is in the cutoff, so open. Then PMOS is in the linear, that is in the non-saturation mode, therefore it is representing as resistance RP. It is the equivalent circuit, so therefore output is equal to VDD only. Then for the second, when input is increased from VTN to VDD by 2, this NMOS transistor is also switched on and this NMOS transistor is went into the saturation region and PMOS transistor will be in the non-saturation mode. Then saturation mode is representing as current source, non-saturation is representing as the resistor. Now output voltage is reduced than the previous case in the region B, that is output is equal to less than VDD and greater than VDD by 2. Then in the next input is increased, that is it is taken at VDD by 2 value, then both transistors will be in the SAT. It is a maximum current flowing in the circuit in that region, then output is also equal to VDD by 2. So output drops and output is equal to VDD by 2 in the region C. Now in the region D, input is still increased from the VDD by 2 to VDD minus mod VTP. Then NMOS is in the non-saturation region and PMOS is in the saturation region. Therefore, PMOS is representing as current source. So, it will produce the output value as less than of VDD by 2. And in the fifth region, that is Vn is taking as VDD minus mod VTP to VDD value, then PMOS transistor is off. Therefore, NMOS is on and it is having the discharge path. So, output is equal to logic 0. That is the region of E. So, this is the 5 regions of operation and its equivalent circuit, transistor's behavior and output value for the inverter circuit. This is the operation of the CMOS inverter in 5 regions. Now, by using these 5 regions of operation, we can plot transfer characteristics by superimposing the NMOS transistor current curves over the PMOS transistor current curves. If we draw that will be look like this. Before that, just see the transfer characteristics, how is the shape. Later we can see how that shape was occurred. Now the shape of the transfer characteristics is, this is the transfer characteristics shape. That is, when Vin is equal to low, output is equal to VDD. Then Vin is equal to VDD, output is equal to 0. So output is reducing from VDD and it is reaching to 0 value in the region 5. Now, this was drawn based on the overlapping of the current characteristics of NMOS and PMOS transistors. So, see here in this graph, V out is taken on the x-axis, IDN is taken on the y-axis, IDS versus VDS value. This is the graph which is representing with the solid line is for the NMOS enhancement characteristic of the CMOS inverter circuit, and this is a dotted line is representation of PMOS. So, PMOS curves and NMOS curves. By superimposing these for a VGS value of equal value, that is when VGS is equal to 0, when VGS is equal to 0.5, when VGS is equal to 1 and etc. So, VGS is increasing, Vin is increasing. Then having a superimposing of these two characteristics of this, and now taking these overlapping points of NMOS and PMOS characteristics and plotting these points, we will get this transfer characteristics. So, observe these transfer characteristics in the 5 regions of operation. Then in the 5 regions of operation, this transfer characteristics will be like this. That is, in the region A, the transistor T1 means NMOS. NMOS is off and PMOS is on. Okay. So, their output is equal to VDD and it is slightly, because it is a changing value. So, it is equal to VDD and it is slightly changing. Then the second region, what will happen? This VDD is reducing and it will reach to the VDD by 2 in the region B. That is in the region B. And region C is at one point, that is VDD by 2, at Vin, V out is also VDD by 2. Now in region 4, that is at D, output is still reducing as input is increasing its value. Then in region E, the output is reached to 0 because input is reached to VDD. So first region 0 to VTN is the region 1, VTN to VDD by 2 is region 2, at VDD by 2 is region 3, and VDD by 2 to VDD minus mod VTP is region 4, and VDD minus mod VTP to VDD is the region 5. These are the input ranges, these are the transistor conditions, then output voltage is equal to this. This is the transfer characteristics of, or DC transfer characteristics of CMOS inverter. Let's see along with the output voltage how the current exists in this CMOS inverter circuit. Now this is the transfer characteristics which we have seen, V out versus V in. The below graph is representing current IDS in the inverter with respect to V in. We have seen out of all the 5 regions, region C is having of maximum current because both transistors are in the saturation region in the region C. So, the region C is having of maximum current here, and from region A to region C, the current is increasing, and from region C to region E, current is decreasing as output voltage is reducing here. So this is the current characteristics of CMOS inverter. The maximum current and equal current in both NMOS and PMOS transistors will exist at the region C point, that is IDS is equal to IDSN is equal to IDSP. The current in the both transistors is equal, that is a maximum saturating current value. At this point, the output and input are also equal, that is called as V in is equal to V out is equal to VDD by 2, where it is calling as V inverting. V invert, that is, it is called as switching threshold. Switching threshold means at this value, actually, the both output values for the 0 and 1 will be separated. Till now we have seen in CMOS inverter operation, its circuit, construction and its transfer characteristics. Now let us check its sizing. NMOS and PMOS transistor sizes for getting of V invert is equal to VDD by 2. That means V in is equal to V out is equal to VDD by 2. To get that, what should be the size of the NMOS and PMOS transistors? Here sizing is an important issue to get transfer characteristics of symmetric curve. Symmetric means V in is equal to V out is equal to VDD by 2. To get this, if the characteristics are like that, then those are called as symmetric characteristic. To get that, transistor sizes should be different of the NMOS and PMOS. In this region, both transistors are in saturation, that is taking a third region. Then current is also equal and it is a maximum. Its equivalent circuit is representing with both current sources, and saturation current equation representation is this: IDS is equal to beta by 2 into VGS minus VT whole square, where for NMOS transistor this beta is representing as beta N, and for the PMOS transistor beta is representing as beta P. So take the currents of IDSP and IDSN and substitute VGSP and VGSN here, and substitute beta N and beta P here, and get the value for V in value. V in, that is equal to V invert value. Now, by taking off saturating current of PMOS transistor, sat current of PMOS transistor, that is beta P by 2 into VGS. VGS is equal to V in minus VDD, which we have seen already, minus VTP whole square, and sat current of NMOS transistor is equal to beta N by 2 into VGS. VGS is V in here minus VTN square. These two are VGS values, VGSP and VGSN. Because these two are equal, substituting these two in this equation and simplifying this, we will get V in of this equation. V in is equal to, this is the equation value. Now, to get V in is equal to VDD by 2, we have to assume that beta N is equal to beta P and VTN is equal to mod VTP. Threshold voltage of NMOS and PMOS transistors are equal, and beta N is equal to beta P. If we substitute these two in this above equation, we will get Vn is equal to 0.5 VDD. There, V out is also 0.5 VDD in the region C. Therefore, it is calling as V inverting point symmetric characteristic. So, symmetric characteristic means Vin is equal to V out is equal to 0.5 VDD. To get this, what is assumption? Assumption is beta N is equal to beta P. This is important now. When beta N is equal to beta P, when it will happen? Based on the definition of the beta N and beta P, let us check this when these two will be equal. So, beta N is equal to beta P means what? Beta N definition is equal to epsilon insulator epsilon naught mu n by d into Wn by Ln. Similarly, beta P is also same with the change of mobility mu P, Wp and Lp. If we equate these two, d will be cancelled, epsilon insulator epsilon naught will be cancelled because the equal values. So mu n Wn by Ln is equal to mu p Wp by Lp. Then Wp by Lp is equal to mu n by mu p into Wn by Ln, where mu n is greater than of mu p, that is mu n is equal to 640 and mu p is equal to 250. By substituting this, we can get Wp by Lp is equal to 2.5 times of Wn by Ln. We are taking approximately, it is equal to 2.5 times. That means to get symmetric voltage transfer characteristic, or Vin is equal to Vout is equal to VDD by 2. Size of PMOS should be equal to 2.5 times of size of NMOS. This is the conclusion. So size of the PMOS and size of the NMOS relation should be this to get the voltage transfer characteristics of symmetric. So size of the PMOS should be greater than of size of NMOS of the 2.5 times. This is the sizing value. Now let's check transfer characteristic by changing its size. First, taking beta n is equal to beta p, that is symmetric characteristic. Then its transfer characteristic is represented like this. Now if beta n by beta p is increased or decreased, greater than 1 or less than 1, that means if beta n is greater than of beta p, that means what? NMOS is greater than of PMOS size. That means good NMOS, it is representing as good NMOS. If NMOS is good, then transfer characteristic is shifted inside of the or inwards of the symmetric characteristic. So this is the characteristic, that means this is for the good NMOS characteristic. Then if beta p is greater than of beta n, means PMOS is greater than of NMOS sizes, then that is called as good PMOS, means PMOS size is more. Then transfer characteristic is more outside. So this is the characteristics for good PMOS. Means when we have plotted the V invert points. So V invert is at point 1 for the symmetric, then that V invert point is reduced or V invert point is increased. For good NMOS, V inverting point is reduced. For good PMOS, P inverting point will be increased. That means voltage at point 2 is less than of point 1 and at point 3 it is greater than of point 1. This is the conclusion of this transfer characteristics and sizing. That means if you want to shift V inverting point, we can shift by changing the sizes of the transistors. Let's check this quiz. First one, in CMOS, if both the transistors are in saturation, then they act as saturation region. How the transistor is acting as current source. So answer is current source. In CMOS, beta n is equal to beta p. Then V invert is equal to exactly equal to VDD by 2. So that is 0.5 VDD. Next, so it is a problem. In the CMOS inverter circuit shown, if the transconductance parameters of the NMOS and PMOS are given as. So directly here mu n COX into W by n is nothing but beta. Beta is given but representation is given as Kn Kp. So beta n is equal to beta p is equal to given, that is 40 microamperes per volt square, and their threshold values Vt is equal to 1 volt. Means threshold value for the NMOS and PMOS are same, that is equal to 1 volt. And in the circuit, Vn is given as 2.5 volts, VDD is given as 5 volts. Means Vin is equal to VDD by 2 is given. So when Vin is equal to VDD by 2 is given, in which region this CMOS inverter is operating? In the region C it is operating, region C. So when it is in the region C, what is the current of the PMOS and NMOS I? It is equal amount of current and it is a maximum. So IDS SAT is the current. What is the formula for that? Beta by 2 into VGS minus VT whole square. So VGS for the NMOS, if we find IDSN, it is equal to IDSP only. So therefore, find the IDSN. That is beta. Beta is given already 40 by 2 into VGS is Vn. Vn is equal to 2.5 minus Vt is given as 1 whole square. So that is 20 into 1.5 square microamperes per volt square already given. So the answer will be in terms of microamperes. So 20 into 1.5 whole square, it will be 45 microamperes. So answer for this is 45 microamperes. Take this as assignment question. It is nothing but complete the below table with numerical values. The operation of the CMOS inverter for these Vin values, find the Vout and condition of NMOS and PMOS regions. This is also assignment question. This is also giving based on the characteristics. So do this as assignment question. Follow these two textbooks. One is a Pucknell textbook and second one is the Neil West textbook for this topic. Summary. Till now we have seen CMOS inverter construction, means it's a circuit, and then its operation we have seen. In 5 different regions we have seen. To draw the transfer characteristics and to have the symmetric characteristics, we have seen the sizing of the PMOS and NMOS. So size of the PMOS should be equal to 2.5 times of NMOS. That is a conclusion to get the symmetric characteristics of the CMOS inverter. I hope you understood this CMOS inverter. In the next lecture, we will see BiCMOS inverter. Thank you.